Welcome to DevSecOps, the podcast created by Ben, Moiz, and Sneh, and powered by CyberViewPoint. Welcome to CyberViewPoint Originals, the podcast where we decode modern cybersecurity strategies and real-world defenses for today's digital world. In this deep dive, we're stripping away the abstraction layers. We're diving into the engine room of modern tech, containers and Kubernetes. We're going to explore how to secure the software supply chain and lock down the orchestrator that runs the world's infrastructure.
And it's an absolutely essential conversation to have. The speed at which containers and Kubernetes have been adopted across nearly every industry has, it's completely outpaced the maturity of the security best practices.
Yeah.
So many organizations, and maybe even yours, are operating under this false perception that a container is some kind of secure sandbox, just because it's a new layer.
And that false perception, that idea of security through abstraction, that's exactly what attackers like Captain Hashjack and their crew are banking on. They are absolutely scouting environments using OSINT to figure out what version of Kubernetes you might be running.
Oh, for sure.
And then they're just looking for those easy default misconfigurations that basically scream, come on in.
Our mission today is to systematically expose those layers of abstraction. We'll look at the famous 4Cs model code, container, cluster, and cloud, and really detail the threat-based guide you need to build true continuous defense in depth across the entire cloud-native environment.
Right.
We have to move beyond just thinking about container isolation and start looking at the control plane itself as the real primary target.
Okay, let's unpack this starting at the most fundamental level then.
Right.
The container itself. If you've spent years working in a traditional data center, dealing with server virtualization, you might assume containers are just small virtual machines, little micro VMs that offer that same kind of hardware separation.
Right.
Why is believing that actually a dangerous foundation for security?
It's dangerous because it's a fundamental misunderstanding of how the technology actually works under the hood. We need to be crystal clear about this. Containers are not full-fledged virtual machines. Think about traditional server virtualization, with Hyper-V or VMware. That technology uses a hypervisor to actually emulate the physical hardware. Then it boots a full independent guest kernel inside that virtual environment.
So if we use our construction analogy, that's kind of like having several separate houses built on one physical plot of land. Each house has its own plumbing, its own wiring, its own foundation, and a separate locked front door. Even if I compromise the roof of one house, I haven't necessarily gotten into the next one over.
That's a perfect contrast. Containers, by comparison, use what we call operating system level virtualization. They are just constrained processes running directly on the single shared host kernel.
The shared kernel, that's the key.
That's the key. So instead of full hardware emulation, they rely on Linux kernel primitives to sort of fake the isolation. They share all the kernel pathways, which means if that kernel is exploitable, or if the kernel's isolation primitives are misconfigured, that security boundary can be incredibly slim.
And a breach can affect every other container on that node. So if the houses are VMs, then containers are more like apartments in a single building. Everyone shares the same foundation, the same plumbing, and critically, the same shared utility line that connects to the outside world, the kernel. If one tenant causes a catastrophic failure in that shared infrastructure, everyone is potentially affected. So let's get into the two Linux primitives that create this crucial, yet kind of porous isolation boundary.
The two core pillars here are namespaces and Cgroups. First, namespaces provide the isolation by giving the containerized process a restricted view of the host system. It controls what the process can actually see.
An illusion of separation.
It's totally an illusion of separation. So it gets its own unique set of process IDs or PIDs, its own network stack, its own user IDs, and its own mount points. The kernel is still one single thing, but the process only sees its specific restricted slice of that world.
That makes sense for separating the views, but what about resource management? If one apartment starts running 12 washing machines at once, they could overload the shared utility lines for everybody else in the building.
And that's the role of Cgroups, or control groups. Cgroups manage and limit that resource usage. This is absolutely essential for preventing a single container from, say, initiating a resource denial of service or DOS attack.
Right.
And make sure one greedy application can't starve the host node or the other containers by just eating up all the CPU or memory or I/O bandwidth.
Yeah.
Cgroups are critical for system stability, but they're not fundamentally a security isolation mechanism in the same way namespaces are.
Now let's get to the most common, and I would argue probably the most dangerous security misconfiguration that still plagues container deployments today. running as root.
Ah, the root problem, yes. Despite all the advancements we've made, processes inside a container very often still run with root user privileges by default.
Still.
And even though Linux containers implement a degree of user ID mapping and permission reduction, the process is still operating as UID 0. The kernel just treats the root user differently. It allows access to all sorts of capabilities and pathways that a non-root user would just never be granted.
So if that process escapes, it's already running as root on the host. And that is the ultimate prize for Captain Hashjack.
It's game over.
We saw this reality demonstrated with exploits like CVE 2019-5736, that famous runc-proc-selfx vulnerability, which allowed an attacker to overwrite the host runc binary. It absolutely thrived on the container's ability to execute commands as root internally.
So what's the simplest, most actionable defense against this? It's really just adhering to established Linux security practice.
It's preventing the processes from running as root inside the container. That sounds deceptively simple, though.
It is the single most effective security measure, and you'd be surprised how often it's overlooked. We should be enforcing non-root execution by setting the container's security context to run as non-root.
Okay.
True, or, explicitly enforcing a high UID, something greater than 10,000 for those processes.
Right.
This adherence to the principle of least privilege immediately neuters so many common container breakout attacks that rely on manipulating privileged files.
But doesn't running a container process as, say, UID 1001 create a ton of operational friction for developers? I mean, if they expect to see a standard user like root or the www data for log file ownership or accessing mounted volumes, now they have to debug these complex permission issues because they are using some non-standard UID. What's the trade-off there?
That's a completely valid pain point, and it's why security teams often get so much pushback. The trade-off is friction for security. When you enforce a high, non-standard UID, you're minimizing the risk of a UID collision.
A collision?
Yeah. If the container's UID accidentally matches an equivalent privileged UID on the host, and it can reach files through a mounted volume or a shared namespace, that resource access can enable a container breakout. The slight operational inconvenience of managing file permissions inside the container is a tiny price to pay for blocking a massive number of known breakout vectors.
That brings up the need for more advanced sandboxing. If you have a highly untrusted workload, say a public API that processes user-supplied, unsanitized complex files like PDFs or videos, which are notorious for having escapable bugs, you might need a stronger boundary than standard Linux containers can offer. You need more than just the apartment building analogy. You really need separate houses.
Absolutely. And when standard namespaces and Cgroups aren't enough, we turn to hardware-backed sandboxing. The primary example here is Kata containers.
Kata containers?
Yeah, it's a specialized runtime that intelligently takes container technology and wraps each one in a lightweight KVM virtual machine.
Now, that sounds like it would have a heavy performance hit. Where's the balance point between that container speed and the VM isolation?
The balance is achieved because KVM virtualization is so highly optimized. And while there's a slight startup overhead compared to a pure runc container, Kata gives each container its own dedicated guest Linux kernel inside its own little VM.
So you get true hardware isolation.
You get true hardware isolation. The hypervisor now acts as the true security boundary, not the host kernel's primitives. This is ideal for hard multi-tenant systems, like a managed hosting provider, or environments processing genuinely untrusted, complex data where, zero-day vulnerabilities in the kernel are a constant documented threat. It's really the strongest boundary you can achieve without sacrificing the container image workflow entirely.
Okay, so we've locked down what the container is and how it runs, but the bigger question remains, how do we make sure we're not baking vulnerabilities into the very image we're supposed to trust?
And now we shift our focus to the source of the container itself, the software supply chain. And it's just a massive, complex attack surface.
Right. It's
not just your application code. It's this whole web that includes the base image, all the installed operating system packages, application dependencies, open source artifacts you pull from public registries.
And any external repositories you pull data from during the build process.
Right. It's huge.
This is the classic garbage in, garbage out problem, but it's magnified by the scale and speed of modern DevOps. You might secure your perimeter and your orchestrator, but if Captain Hashjack can sneak malicious code into your trusted source software, like the Sunburst attack demonstrated so powerfully, they have an internal foothold that bypasses all your network controls.
The Sunburst attack was a monumental lesson for all of us because it showed that attackers are specifically targeting the build pipeline. They got into the SolarWinds build infrastructure and they just stayed hidden for months, modifying the output before it was signed and distributed.
Yeah.
This proved that build systems, the CI/CD pipelines, are often not subjected to the same level of security scrutiny or intrusion detection or even monitoring as production systems are. And this is despite them delivering code directly to production and to your customers.
And this ties into a really fascinating sort of counterintuitive concept known as reverse uptime.
Reverse uptime, yeah. It describes the idea that the risk of an application being compromised actually increases the longer it runs without an update or a rebuild.
Right. Applications don't get more secure with age.
Not at all. The base components, the libraries, the OS packages, they all become progressively more out of date and therefore riskier the longer the container image is deployed without being refreshed. We have to prioritize continuous rebuilding, not continuous patching of these long-lived images.
So how do we shift left and proactively secure the image before it even hits the registry? Where does that journey start?
It absolutely starts with minimalism. This is key to image hardening. The goal is to reduce the attack surface by using the leanest possible base images. We really advocate for images like distro list,
which has only your application and its dependencies.
Exactly. Or even Scratch, which is truly empty, designed for statically compiled Go or Rust binaries.
What specifically is the security benefit of removing everything but the necessary runtime? I mean, what does that really get you?
Well, when you use a standard Alpine or an Ubuntu base image, you inherit hundreds of utilities. Shells like bash, package managers like apt or apt, text editors, common utilities. If you eliminate those, you eliminate the tools an attacker relies on during their post-exploitation phase. If you don't include bash, an attacker can't use bash. That immediately neuters a whole class of common command injection and exploitation techniques that rely on a shell being present.
So you're just drastically reducing the number of potential CVEs in your image by getting rid of unnecessary user space components.
Precisely.
Once we have that minimal image, the next step has to be mandatory automated scanning. We have to check all our ingredients, whether they are OS packages or third-party libraries.
Correct. Automated vulnerability scanning tools, things like Anchor, Trivy, Claire, or the OWASP dependency check, they must be integrated directly into the continuous integration, the CI process. We cannot wait for the image to be running in production to check for CVEs.
You have to enforce mandatory gates.
Mandatory gates. If a high or critical vulnerability is detected, the build must fail. And developers have to fix the dependency before the image is even pushed to a registry.
And part of that ingredient check is creating a full SBOM, or software bill of materials. Why has the SBOM suddenly become such a mandatory piece of compliance?
An SBOM is a crucial step toward transparency and proactive risk management. Tools like SIF can generate this, basically a packing list of every single software artifact, every dependency, and their versions that are present in the final image.
Right.
And this transparency is vital because when a new zero-day vulnerability, a new CVE is announced, like we saw with Log4j, teams don't have to scramble to scan every running container. They can just query the repository of SBOMs to immediately identify every application that depends on that vulnerable component. It drastically accelerates remediation time.
But even with scanning and SBOMs, the deeper philosophical problem remains this issue of trusting trust, which is something that's been studied in computing since, the 1980s. How do we verify that the code we're running wasn't maliciously implanted earlier in the chain, even if it looks clean now?
That's where content signing and cryptographic supply chain verification come in. The most fundamental defense against malicious injection is to implement robust image signing.
Like Docker Content Trust.
Docker Content Trust, or DCT, is a basic mechanism. When it's enabled, the Docker daemon will only download and execute images that have been cryptographically signed by a trusted developer. If the final image manifest hash doesn't match the original signature, the deployment is just denied.
That seems fine for checking the final artifact, but the critique we often hear is that attackers are getting smarter. They don't just compromise the final image, they compromise the tools that build the image, just like we saw with Sunburst.
Which is exactly why we have to move to frameworks that sign the process, not just the product. InToto and TU, the update framework, are standards designed for this kind of verifiable supply chain integrity. They go way beyond just signing the final container image. They checksum and sign every single step of the CI/CD pipeline, from the source code checkout to compilation to testing all the way to the final image push. It creates verifiable metadata about the entire build process.
So an organization is creating verifiable signatures for everything, from the machine that performed the compile to the timestamp of the tests to the final artifact. But what is the operational burden of adopting this level of signing? It sounds like it could dramatically slow down deployment.
It does require operational rigor, which is why it often requires that culture shift we'll talk about later. You have to manage signing keys, integrate them securely into your CI system, and handle key rotation, which is complex.
Right.
However, the security benefit outweighs this overhead for high-trust workloads. This verifiable metadata, often stored in transparency logs like Record, establishes a really strong web of trust. It forces Captain Hashjack to compromise not just one build server, but the entire, often geographically distributed, signing infrastructure. It just significantly raises the cost and complexity of a successful attack.
That's a powerful barrier to entry. Okay, we've secured the container image itself. Now let's zoom out to the orchestrator. Kubernetes. This is where the complexity just goes through the roof.
Yeah, and we need to set the stage with the 4 C's of cloud native security model. It's the foundational framework. The C's are codes, your application, container, the runtime and isolation, cluster, Kubernetes itself, the brain, and cloud, the underlying infrastructure like AWS or Azure.
And security must be managed continuously at every layer.
Continuously.
Yeah.
It acknowledges the shared responsibility model. You can't just rely on hardening the container if the cluster defaults are wide open or if the underlying cloud IAM is completely misconfigured.
Let's focus on the brain of the cluster, the control plane components. If Kubernetes were a city, where is the most critical attack surface? Where's the air traffic control tower?
That would be the API server. It is the single most critical component. It is the front end for the entire cluster. All human commands, all automated interactions from the kubelet on the nodes, all controller loops, everything goes through it.
So any admin interface connecting to it has to be heavily restricted and properly authenticated.
Absolutely. A huge percentage of Kubernetes vulnerabilities target authentication or authorization flaws right there in the API server.
And the API server relies on etc. That distributed key value database stores everything: the cluster state, the configuration, and most critically, all the Kubernetes secrets. If an attacker breaches, etc., it really feels like game over.
If Captain Hashjack gains read access to etc., it absolutely is game over. It's the data store for all cluster state and secrets. The highest risk deployment option we see is often when organizations run etc. as self-hosted pods inside the Kubernetes cluster.
Which exposes it directly to the container network.
Exactly, to the CNI.
Yeah.
An accidental RBAC misconfiguration could then allow an attacker to pivot from a compromised pod and just tamper with the whole cluster state via etc.
So what's the immediate non-negotiable action needed for protecting secrets and that etc. backbone?
First, secure the network path to etc. Ideally, you isolate it entirely outside the CNI if you can. Second, never rely on plaintext storage. While Kubernetes secrets are base 64 encoded by default, that is not encryption.
It's just obfuscation.
It's just obfuscation.
Mm-hmm.
You have to configure the API server to ensure secrets are encrypted at rest, and etc., using key rotation mechanisms. Better still, use external key management solutions like KMS or HashiCorp Vault that integrate via CSI drivers so secrets are never natively stored in etc. in any form.
And audit logs.
And finally, yes, enable and retain API server audit logs for a suitable period, say 30 days, to track every single command and access attempt.
Now let's dive into the defensive layers, starting with layer 1, least privilege using RBAC. This governs who and what can actually talk to the API server.
Role-based access control, or RBAC, is the primary mechanism for enforcing least privilege. And this applies not just for human users accessing the cluster via kubectl, but crucially for automated workloads via service accounts. A service account represents the application's identity inside Kubernetes, allowing it to interact with the API server.
And this is where we find that crucial piece of attack treasure, right?
Indeed. By default, Kubernetes automatically generates and mounts a JSON Web Token, a JWT, for the service account into the pod at a standard, well-known location. This token is an adversary's treasure because it enables identity spoofing.
Right.
An attacker who compromises the pod can steal that JWT to communicate with the API server, or even use the workload identity to pivot into cloud integrations, like S3 buckets or database access, if those connections are exposed.
So the goal then is to restrict what the service account can do with that token to the absolute bare minimum required for the application to function.
Exactly. We have to audit and restrict the permissions associated with default service accounts. Developers should never, ever be given cluster admin access casually, even for debugging. The ideal state is to use namespace-level service accounts with ultra-granular permissions. And tools like Audit to or Back can significantly mitigate this burden.
Audit to or Back, that sounds powerful, but how does it work in practice? Manually generating these roles seems well, impossible for a large application.
Manually defining roles often results in overly broad access because, nobody wants to be the one to break a running application. Audit Drawback works by taking the actual observed audit logs from the API server, the record of all the calls the application actually made.
I see.
And it automatically generates the minimum necessary RBAC roles and bindings. It shifts the burden from guesswork to evidence. You deploy the app, let it run for a while, observe its API usage, generate the role, and then enforce it.
And that ensures the service account token only has access to, say, get pods in its own namespace and nothing more.
Nothing more.
That significantly reduces the window for lateral movement. Okay, moving to layer 2, the pod security context. This is where we control those underlying Linux kernel primitives we talked about earlier.
The security context is fundamental for isolation. It's how we enforce critical rules on every single deployment. The core principles are about limiting privilege and host access. 1. Ensure the pod is never run as privileged. True, and that allow privilege escalation. False is set.
Right.
2. Restrict host access. This means setting host PID, host IPC, and host network all to false to prevent sharing the host's process list or communication mechanisms or its network namespace.
And we absolutely have to talk about preventing host path mounts. That's a classic notorious attack vector for container breakout.
Absolutely critical. You must prevent writable host path mounts, especially mounts like varendocker.sock, which grants access to the host's Docker daemon.
Which is a huge no-no.
Huge. If an attacker gains remote code execution in a compromised container and finds they can write to that Docker socket, they can simply use the Docker client from within the compromised container to start a new privileged container on the host node. That results in immediate host root access. It's a direct, unmitigated path to full system compromise.
Beyond these basic file system and privilege controls, we can also fine-tune kernel access using capabilities and SecComp. This gets really deep into the operating system.
It does. Linux capabilities break down the monolithic concept of root into these granular privileges, like the ability to open raw sockets, capnitra, or change the system time, capsys time. As this practice, workloads should actively drop unused capabilities using capdrop all and only explicitly request the few capabilities they actually need.
So if your application doesn't need to sniff network traffic, drop capnitra.
Right, to prevent a malicious process from doing so.
And SecComp profile enforcement, what's the practical benefit of that?
SecComp secure computing is even deeper. It enforces a profile that restricts the list of allowed kernel system calls, or syscalls. Container runtimes usually ship with default SecComp profiles that block dangerous low-level kernel access, like mounting file systems or invoking system reboots. And this has historically prevented many zero-day attacks that rely on finding a vulnerability in some obscure or risky system call. You have to ensure these profiles are enforced cluster-wide via the security context. If you skip SecComp, Captain Hashjack suddenly has a much wider array of kernel functions to try and exploit.
Finally, layer 3. Network policies. We've configured isolation inside the container, but why is an internal firewall required if we already have namespaces separating our services?
Because Kubernetes, by its very design, assumes a flat, open network model. Pods are randomly assigned IP addresses and placed on nodes, but a prerequisite for any Kubernetes network implementation is that all pods must be able to communicate with all other pods across the cluster by default.
That is the complete antithesis of zero-trust architecture. If one front-end web container is compromised, the attacker has a free path to traverse the entire internal network, including the database and the API server.
Precisely. Network policies introduce internal firewalls inside the cluster. They allow administrators to use labels or namespaces to define which pods are allowed to talk to which other pods. You can enforce a deny all by default policy and then only explicitly permit traffic between the front end and the database on, say, port 5432.
So if an attacker gets RCE in a front-end COD,
a network policy can prevent them from initiating internal network scanning, that lateral movement, to reach the control plane or any unauthorized services.
But doesn't implementing a complex layer of network policies introduce significant operational and maybe performance overhead? How do you ensure you haven't accidentally blocked legitimate traffic?
It is complex, and it requires continuous validation, often using network visibility tools. There can be a slight overhead depending on the CNI plugin you use, Cilium, Calico, whatever, but the security benefit dramatically outweighs the performance cost. The bigger challenge is really the development friction. Policies have to be treated as code and reviewed carefully because blocking the wrong port can halt an entire microservice chain. But without them, you are betting your entire data center on the initial perimeter holding, which is a bet you will eventually lose.
Okay, so to properly defend a cloud-native environment, you have to continually assess your configuration from Captain Hashjack's perspective, right?
Absolutely. The main objective, once a foothold is established in a container, is always one of two things: container escape or pivoting across the cluster network to elevate privileges.
Let's talk about the common low-hanging fruit when attacking a container. What are the common breakout scenarios that you see?
They fall broadly into two types: configuration exploits and runtime exploits. For configuration, attackers are hunting for overly permissive volumes or exposed credentials. This includes exploiting poorly secured external network file systems mounted as volumes like NFS or CIFS, which might allow an attacker to write executable files to the host.
Right.
Or they might look for accidental exposure of cloud credentials via the worker node's metadata API, especially in non-cloud provider-managed clusters. And that mounted service account token we discussed is the fastest path to the API server.
But the more sophisticated attacks go after the heart of the system, the kernel or the container runtime itself. How do they weaponize those?
We mentioned historical examples like CVE 2019-5736, the Runk vulnerability, which was a landmark example of exploiting the runtime to get host root access. But attacks are becoming more subtle. A contemporary and highly effective technique is runtime modification.
Runtime modification?
Yeah, attackers can inject a malicious sidecar container into an existing deployment using a compromised configuration or via a malicious mutating admission webhook.
A mutating admission webhook is often used legitimately to inject monitoring or logging sidecars. So Captain Hashjack is just weaponizing these normal infrastructure utilities.
Precisely. If they compromise the control plane's webhook, they can ensure that every new pod that gets launched automatically receives an extra container, often hidden, that performs enumeration, observation, or persistence tasks. This demonstrates that configuration integrity must be protected just as strongly as runtime code integrity.
This brings us to a crucial point. Why is static image scanning, no matter how thorough it is, ultimately insufficient for real-world defense?
Because security isn't just a checklist you do at the door. It's continuous. Vulnerabilities can be exploited at runtime, or an attacker can introduce unexpected behavior, what we call drift, even in a container that passed a clean scan.
An example.
For example, an attacker might compromise a dependency, and that dependency then executes a network call to a known malicious IP address. The image scan was clean, but the behavior is hostile. A perfect image doesn't guarantee perfect non-malicious behavior. We need real-time eyes and ears.
This is where intrusion detection systems, IDS, step in as the crucial last line of defense. And the modern approach in Linux centers around this powerful kernel technology that bypasses a lot of traditional user space overhead.
That technology is eBPF, the Extended Berkeley Packet Filter. eBPF is revolutionary. It's a fast in-kernel execution mechanism that allows security tooling to monitor low-level system calls directly from the kernel space without having to move data back and forth to user space.
Which means minimal performance impact.
Minimal performance impact. And tools like Falco leverage eBPF to monitor these system call streams and define rules that detect unauthorized activity based on behavior.
So instead of trying to catch known malicious signatures, we're defining what normal behavior is for a workload and then alerting on any deviation from that. Give us a few examples of what Falco would detect.
The rules are all behavioral. For instance, if an image is deployed as a web server, Falco knows that image should only be listening on port 80 or 443, and it should never spawn a shell.
Right.
So Falco alerts on events like, the shell was executed in a container that has no shell defined in its deployment manifest, or a process attempted to modify a file outside of its designated writable directory, or an application attempted a socket connection outside its listening context. By combining the system call data with the granular metadata from namespaces, the IDS has this rich context to make really accurate detection decisions.
That seems so much more robust than traditional signature-based detection. But if Captain Hashjack is successfully hiding and attempting lateral movement, we can bait them with decoys, can't we?
Yes, we can strategically deploy honeypots. A honeypot is essentially a decoy service, maybe a fake database or an old vulnerability scanner, deployed as a dedicated daemon set on every single node. These services are configured to look highly valuable, but should never legitimately receive any internal network traffic.
So if an attacker gains remote code execution and, as is predictable, starts scanning the internal CNI network looking for their next pivot point,
They might hit the honeypot. That simple HTTP or SQL connection attempt writes to a dedicated log, which instantly triggers a high-priority, zero false positive alert to your SOC or your SIEM. This catches the attacker in the act of internal reconnaissance before they even find a real asset.
Yeah, honeypots are often the most reliable way to detect that lateral movement across the cluster network.
They really are.
Once an incident is detected, the forensic clock starts ticking. But forensics in a containerized environment is uniquely difficult, right? Because of the ephemeral nature of pods and that shared kernel.
The ephemeral nature of pods already complicates forensics.
Yeah.
The evidence might just be gone before you can even log in, but the core difficulty really lies in privilege. Because all containers share the host kernel, a root user who has successfully escaped into the host process namespace can potentially dump the memory of any other process on that node.
And that means they can steal secrets stored in memory, like high-entropy API tokens, database credentials, or in-flight encryption keys.
Exactly. And if this happens, your auditing logs and your real-time alerts are your only true record of what occurred, because the container or the host memory state might be wiped clean.
So we can implement all the best security tools in the world, Falco, Kaida, OPA, but security failure often stems from cultural or organizational gaps, doesn't it?
It really does. The transition to DevSecOps requires a true cultural shift, which often involves some painful organizational restructuring.
It's about integrating security from the very early stages of development, that definitive shift-left mentality, rather than treating it as some final hurdle or a dreaded checklist item right before deployment. Leaving it until the end is not only a critical mistake, but it's wildly expensive to fix.
We often visualize this using the organizational pyramid. It stresses that tools and policies are at the top, but the foundation is built upon individual people, teams, and communication.
Right.
Organizational structure, cross-skilling, and education making developers into security champions. Those are the foundational components that underpin successful security policies. If the development team doesn't understand why they need to run non-root, the policy will just be bypassed or ignored.
And automation is the engine that drives this culture change by reducing all that painful human friction.
Automation is absolutely key because it reduces the chance of human error and it minimizes the time spent by development teams finding and fixing issues. Integrating automated checks like SAST and DAST directly into the CI/CD pipeline accelerates vulnerability detection and remediation so much earlier on.
So developers get immediate feedback when they commit insecure code, rather than waiting a week for a security review to reject their entire deployment.
Exactly.
Speaking of automation, we need to talk about enforcing these security standards using policy as code. How do we ensure every new deployment adheres to our hardening rules, like requiring SecOps profiles or non-root users, without relying on manual review?
This is where admission control is mandatory. Admission controllers are powerful, mandatory plugins for the Kubernetes API server that intercept incoming requests to create or modify resources. They act as security gates. They can enforce security policies, like requiring specific security context settings or ensuring that no pod runs as a root user. If the policy is violated, the API server just rejects the request immediately.
And the leading tool for abstracting that policy logic is OPA. What makes the Open Policy Agent so effective for cloud-native security?
Open Policy Agent, OPA, is a general-purpose policy engine that unifies policy enforcement across the entire stack, not just Kubernetes. It uses a high-level declarative language called Rego. The benefit is that it completely externalizes the policy decision-making from the application or the infrastructure component itself.
So you can write one policy in Rego that checks your Terraform code, validates your Kubernetes YAML, and ensures your service mesh configs are all secure.
All with the same policy engine.
That universality sounds amazing, but I've heard Rego is notoriously complex to master. How do organizations handle the steep learning curve required to write these policies?
That is the trade-off. While the flexibility is unmatched, the learning curve for Rego is significant. It requires specialized skills. Many organizations start by using wrappers like Gatekeeper, which is a Kubernetes-specific OPA implementation, and they rely on community-contributed policy libraries. They'll focus on crucial denial rules first.
Like deny any deployment that mounts the Docker socket.
Exactly, before attempting to write complex, bespoke business logic policies. The investment is high, but the payoff is consistent, auditable policy enforcement everywhere.
Beyond live enforcement, we also need continuous auditing to ensure our cluster hasn't drifted out of compliance or been manually misconfigured after deployment.
Exactly. Live enforcement only handles what's coming in. Continuous auditing handles the existing state, and that's where critical tooling like Kubebench comes in.
Okay.
Kubebench specifically checks Kubernetes installations against well-known, rigorous best practices, notably the CIS benchmarks, for both master and worker nodes. It identifies configuration errors like improper file permissions for the API server pod spec file, or ensuring, etc., data directory permissions are secured, which are so often overlooked after the initial installation.
And that check is vital because even a temporary manual change to a single configuration file on a node can create a permanent security hole if it's not quickly reverted.
Absolutely. And other tools like Polaris perform auditing of the running workloads, flagging insecure settings and running pods that might violate internal standards, even if they pass the initial admission control check because some subsequent controller mutated the state. This continuous loop of auditing and remediation is really the hallmark of modern DevSecOps.
Finally, let's address the persistent threat of credential leakage. Kubernetes is great at managing secrets once they are inside the cluster, but developers often leak them before they even get to the cluster.
Oh yeah, long-lasting credentials like SSH keys, API keys, database passwords, they are inherently dangerous, and they must be aggressively rotated or, ideally, replaced entirely with temporary credentials. In a managed environment, prioritizing temporary, short-lived credentials derived from a trusted identity provider, like AWS IAM roles for service accounts, over permanent API keys is the strongest defense.
But the source code repository, Git, remains the primary leak vector. We've all heard the stories of leaked API keys found in public repos.
It happens every single day. Secrets often end up hard-coded in configuration files or deployment YAMLs in Git. These version control systems have to be scanned regularly using secret scanning tools, because a single leaked API token can give Captain Hashjack a direct bypass into your cloud environment, completely circumventing all the Kubernetes perimeter controls you spent so much time building.
Your perimeter is only as strong as the weakest credentials stored in your commit history.
That's it.
That was an incredible, comprehensive map of the cloud-native security landscape, moving from the kernel all the way to the culture. We've established that Kubernetes security is far from simple. It's a continuous process spanning image creation, policy enforcement via admission control, and constant runtime monitoring.
And if you take one thing away from this, it should be the need for defense in depth, starting with the explicit assumption that a compromise is inevitable. We've seen that the Kubernetes API is highly extensible, which is great for flexibility, but it also means that components rely on these deep trust relationships secured by internal by 509 certificates.
Which leads to a surprisingly manual and disruptive recovery process in a worst-case scenario where an attacker compromises a trusted node and steals those certificates.
Correct. The security model relies on mutual TLS authentication between control plane components and the worker nodes. If a worker node is compromised and its service certificate is leaked, revoking just that single certificate often isn't enough to fully secure the cluster against a determined attacker.
So what do you have to do?
In many cases, you have to revoke, regenerate, and redistribute the entire chain of system certificates across the whole cluster, a procedure that can take hours and essentially requires restarting all the control plane components. The extensibility of Kubernetes means the failure domain, when you're dealing with certificate compromise, is surprisingly broad.
That wraps up this deep dive into the engine room of modern computing. If you enjoyed this detailed exploration of K8s and container security, stay tuned for more deep dives, where we unpack the strategies shaping modern cybersecurity. Until next time, keep your images small and your privileges smaller.